Okay, before starting, I'd like to recall you some information. In the evening, there will be the social dinner. So the meeting point will be outside this building at 19. There will be also a departure point from the train station in Salerno at half past 19. The restaurant is Lido Risorgimento in Viaggi sul Mare. The cost for each person is 25 euros. Tomorrow instead there will be a tour on the Vesuvio. The meeting point is also outside there at 20 past 14. Of course, please remember that the temperature may be high, so wear light clothes. Thank you. Anyway, if you need any other information, you can ask to the staff, to the queue. Okay. Thank you. So the first speaker of this session is Mir Dardo from the University of Trieste, and he will talk about the non-reciprocal and time-delayed interaction in Bishop model.
Thank you. First and foremost, thanks for the organizers for presenting me with this opportunity. I'm Minir Dube. I'm affiliated to University of Trieste and ICTP. And I'm going to talk about non-reciprocal and time-delayed interaction in the WeChat model, and I hope to explain this title as this talk progress. So today I'm all going to talk about some locally interacting and moving units which are far from equilibrium. And the kind of systems which I'm going to address are kind of biological systems, mechanical systems, chemical systems. So these kind of systems are different from, they are very different in scales and dimensions. So let's see what this system. The first example is a mechanical system. So I'm going to talk about some experiments, and then I'm going to say what the goal of my research topic is. The first example is a mechanical system. So we see here three kinds of rice, and there are three different breeds of rice. So one is a jasmine rice, one is a basmati rice, and one is a sushi rice. And the experiment by Aronson was done that they vibrated this rice grains on a vibrating table, and we see that they kind of form a pattern. So in one kind of rice, which is a basmati rice, we see that the nematic order is of correlated 4 to 5 grains, and in other rice, the correlation in the nematic order is smaller. The next system is biological cells. So these are the cells which are taken from the goldfish. And this experiment was done by Fernando Peruani et al. What they saw that when you keep these cells in a medium, they are able to move, and as they come in contact with each other, they kind of form a cluster, and this cluster move in a common direction. Next system is school of fish or the flock of birds. So we see some interesting videos. These are the sterling birds. It's called the murmuration. It's over the California sky. So they are in thousands of in numbers, and they flock. When they are close to their home, they just form these patterns, beautiful patterns, and they show what is a collective behavior. This is what the beautiful pattern they form. Another example is school of fish that we might have seen. And the fish here we saw is kind of forming a vortex state. So what I'm going to address is that the collective behavior in all these kind of systems. So why collective behavior usually appears? There are some points that in one of the experiments that was shown that by teacher et al. That if there is a fish school or a fish in a tank, and if you keep the food patches in a random places, if they are in a group, they find the food patch quickly, and the individual fish will take more and more time. So the first point is you can have a collective behavior to find the food very quickly. Another use of the collective behavior is attributed as the confusion effect. that when the group is approached by a predator, so they form a pattern which confuse the predator and save themselves. And the third one is, of course, the social behavior that you have to reproduce, so the collective behavior is easy to find mates. And in all these systems, the question or the goal of the research is that we try to address some basic questions in that although these systems are from different scales, is there any, the patterns that we saw, are they any system specific or there are some classes of patterns? What are the underlying principles of this collective behavior? How this agent they interact to form this flock? Because in the flock, one particular agent will not be able to see the entire flock. So how they accomplish this task? And the last point is that I'm very much recently interested in the decision making. So how the individual agent take decisions to perform certain tasks. Like we saw in the foraging that when they are in group, they find the food quickly. So how information they share or what decisions they take to find the food. And so these systems are out of equilibrium in the sense that the momentum in the systems are not conserved, so there is very less we can achieve theoretically. One approach is to study these systems with models, and there were several models which were starting as soon as the computer were used for scientific purposes. We saw that the model by IoT, in the early stages, he tried to explain the schooling in the fish that we saw, that how this vortex appear. Another one was by Reynolds in 1987 that he tried to study the flock of birds. But the major breakthrough came in 1995 with the Wittcheck's model. And what was different of this model is that it gives a quantity which quantify this flocking. Before that, we were just producing some patterns on a computer and trying to see whether they match a real system or not. And by Wittcheck, they gave a quantity which is an order parameter which I explained. It gave a measure of flocking. And later on, Cavana or Peruani or several models, they try to address different phenomena that were observed in a flock. Like Cavana et al., they try to address that how this flock make a collective turn in a very synchronous way. Or by Professor Peruani, that is how they take a continuous turn. That was explained in these models. And I give introduction about the Wittcheck model, which I studied in a little bit detail. So this is the algorithm of the model. So you have n particles in a simulation of box size L by L, and initially they are kept with a random velocity but a constant speed. So each have a random direction. And the rule is that at all time steps, all the agents, they look in their neighborhood of radius r, and they try to take the average direction of their neighbors. So the model says that the neighbors do as the agents do as their neighbors do. And this alignment, when they try to align to their neighbors, this alignment is imperfect due to some errors in calculating the average direction or taking the orientation, so that is given by the noise. And the noise is modeled in the following way. So each agent looks in the neighborhood, it takes the average direction, and it is rotated by some angle theta. So if my average direction is this way, I do not align perfectly, but I deviate by some angle theta. And that theta is chosen from minus pi to plus pi orientation. The main highlight of the model was the order parameter, and it is a average direct, the summation of all the velocities. So if every agent is moving in the same direction, your velocity adds up, and if they're all in a random direction, so they cancel out, and the order parameter is 0. So when the order parameter is 0, it is called disordered state, and if they're in an order and going in the same direction, it is called the ordered state. So these are the simulations of some rods, which just to indicate that how the order and disordered states looks like. So in a disordered state, they are oriented in a random way, and in an ordered state, they are ordered in a one particular direction. I have some simulation movies to show you that. So So we start simulation from a random orientation, and as the mistake mode algorithm is applied, all the agents they converge into a common direction, and this is a favorable condition for the ordered state. So they all go in a common direction at the end. And if the conditions are such that this ordered state is not favored, they are in a disordered state. So this is what happens. So agent starts in a random orientation and they continue to be in a disordered state, so they perform their individual random walk. So they never go in a one particular converging direction. So when this ordered and disordered states are favorable, it is given by the study by the Wilczek et al. So on the y-axis we have the order parameter, and it is on the x-axis we have a noise, and they showed that the system undergoes a second order phase transition from ordered to disordered state as the noise is increased, meaning that in a low noise region the agent can go in a one particular direction, and as the noise increased, after some critical noise value, the system will never attain the ordered state. The second result was that the phase transition, second order phase transition with respect to density. So below some critical density, the system will never attain the ordered state, and above some critical density, the system can attain the ordered state. That was the conclusion from the paper. Now we studied the modification of this model, and we said that in many biological agents, the vision cone, or the way we perceive surrounding, is not a full 360 degree. So there are many examples that gray-headed albatross can see 270 degrees. We humans see 180 degree vertically and 135 degree horizontally. So we restricted this neighborhood of interaction if the agents are interacting via visual view. So the only change was the algorithm was that initially we said that the agents take the average neighborhood direction, and that neighborhood was defined as the radius of circle R. And now with this modification, we see that the agents don't look in the entire surrounding, but only in the vision cone, which is given by view angle alpha. So if I'm an agent, I just look in a region, not in the 360 degrees. And the noise was introduced again in the same way. So we studied this system with some fixed values of parameters, some are different. So speed was kept constant, the noise was constant, radius of interaction was kept constant, and we just varied the view angle to see how the system behaves. And these were the dynamical equations of the system. And we saw that as the view angle is increased, the system can go from the disordered state to the ordered state. So main observations were here that you need some view angle to interact with agents, and after that we saw the ordered state. But we on the counterintuitive, we saw that the optimal order can be achieved by restricting a view angle. So it's one of the reasons that we might have a not full 360 degree view. So we don't need to process so much information to go in a one particular direction. So this phase transition we try to characterize, and there is a one quantity which is called the Binder stimulant. So when you see the phase transition in numerical simulations, it's very difficult to find out exact transition point. So one quantity that helps to pinpoint this transition point is given by the Binder stimulant. And for the first order phase transition, it has a particular property that it shows a dip towards negative infinity at the critical value of the control parameter. And it has a value 2/3 for the ordered state and 1/3 for the disordered state. So we saw that for our simulation that this is indeed true. So this was a critical point, and this concludes that the phase transition that we saw is of the first order. And now we try to introduce a delay. So most of the biological agents, they have a delay in responding to the changing scenario. So instead of updating the position with the velocity which I've calculated, we use the previous velocity. And we saw that there is a qualitative difference between the order parameter and the view angle. In one case, when you don't have a delay, at particular view angle, you reach to the optimum order state. And in one case, we saw that no, it's not reaching the order state, and we were curious about what happens in this region. So in this particular region that looks very ugly from the graph, we saw that the agents they condense into a one in an arrested state. So I just have a video and then I try to explain why that happens. So we start simulation from random positions and velocity, and we keep a view angle, some fixed view angle, and we introduce a one time step of delay. And the particles they are not in an ordered state, but they form a condensate at one particular point, and it's just like a black hole. So whatever particles are trapped within this black hole, they are not able to escape back. And if I accelerate this video a little bit, we will see that all the agents which are going in the black hole, they never come out. And in the end, we just have this stable black hole. So what happens within this is that they are randomly oriented. They are not the randomly oriented, sorry. They're in a kind of a circle which are facing to each other, and then the velocity they cancel out. So the order parameter is zero, but it doesn't capture the steady state which is shown here. So we analyzed this drop from within, and we saw that the distribution is not the uniform one, but they are highly dense at one particular region and they fade away. So there is from the distance of center of mass, we have a particle per unit area, so they have a peak, so they form a dense ring in between, and they fade away. So the mechanism we try to explain is that I just asked Mr. Chairman to be a volunteer. Can you please stand for me? I just asked you to be a volunteer. Can you please stand? So the mechanism is that if he's the agent and I'm the agent, can you fetch for me? Yeah. If I'm an agent, I look at my neighborhood, I'm looking him that he's looking to my back, and he is looking at the same. So we just take a one step forward. I take a one step, and then we turn. So basically, if we have a delay, then we are basically trapped in the same way. But if we don't have a delay, so I look at him, he look at it, I turn my velocity first, and we start to go away. Thank you. So this was a mechanism for that arrested state, and we studied it at what parameter point this condensed state appears. So it appears over a wide range of view angles as well as the noise in the system. And that was the conclusion. And the interesting point that I try to study is now decision making in this system. So in the morning, Dr. Karhasan showed us the examples of supervised learning. And this is a scheme that they use in the machine learning, which is a reinforcement learning. So the scheme is that you have a one particular agent which takes a decision. It's in an environment, and it takes a kind of action, and the environment gives it a percept which consists of two parts. One is the reward and one is the state. So with this reward, the agent learn to take actions given the state in which it is. So the example is that if my goal is to go out of this room, I want to take a correct action towards the door, and the reward can be the distance from the door. So as I start to move towards the door, I get higher and higher reward, and I know that the actions which I'm doing, they are correct. So the main question is to find out the policy, that meaning the given in the state S, what actions to take. And with this scheme, we are trying to learn that how these agents are learning to block, and we have some preliminary results. If you are interested, later we can talk about it. And I thank you very much for your attention. I work with Professor Antonio Celani in ICTP and Professor Melotti in the University of Trieste. And this major work presented was done with my previous supervisor Ahmed Said and Arnav Saha in the University of Pune. And these are my lab mates, Alberto and Matteo. They are very good teachers to me. And thank you for your attention. Thank you.
Thank you for your interesting contribution. Any question or comment? Objection?
So it's interesting that we see murmuration specifically in the two examples you used, fish and birds. which both have very wide fields of vision. Are there examples of murmuration that occur in species with narrower fields of vision that you know of?
It's a good question, but experimentally it's very difficult to control the field of view because it's a one field which is given. I don't know the example where they are narrow, but one few examples that saw that specifically chemotactic or phototactic movements of some plankton. So even if you have a narrow beam of light, they are able to detect, but their sense of detection is not known. So if you have a chemotactic trail which is very thin, they are able to trace it, but controlling this region cone, I really don't know any experiment.
Question?
The task was very interesting, but when you said that the angle theta was random, it was the white noise distribution or just the random angle?
Pardon me?
Uh,
Can you repeat your question, please?
yes, but can you hear me?
Yes, I can hear you.
Okay. When you said that the angle theta was random, it is headed some kind of distribution, for example, the white noise or the color noise, or it was just random?
Okay. Initially, the distribution of angle is uniform, and the noise that we pick is also from the uniform distribution.
Other questions? So if there are no more questions, let's thank the speaker again. The second speaker is Adolfo Cisterna from the Central University of Chile, and he will talk about homogeneous black strings in ADS.
Okay, so first of all, let me thank the organizer for giving me the opportunity to present this work. So this work is more theoretical than the previous one. I hope I'm not going to bore you during my talk. So, I'm going to talk about some compact object solutions that you can construct in some gravity theories that are called black strings. And black strings are mostly constructed in the setup of general relativity without any cosmological constant. And the aim of this work will be to show a simple way to construct this solution also when we include a cosmological constant in an homogeneously fashion way, let's say, okay? So as an overview of the talk, okay, so we know that black holes are the most dense object that we can find in nature, in nature after neutron stars. We know that they are relevant in the range of astrophysical, also in quantum gravity regimes. We know that last year gravitational waves were measured for first time coming from neutron stars, and they give us the important information that the gravitational waves travel at the speed of light, and so on. And we also know that black holes give us the opportunity to test semi-classical gravity and to obtain some quantum gravity effect of nature, let's say. So in general relativity and in fourth dimension, which is the universe we observe today, there are some uniqueness theorems that control the proliferation of black hole solutions. That means that when we are working in general relativity and we are looking for black hole solutions, we know the black hole solution that we are going to find. And these black holes are catalogized in a family called the Kerr-Newman family, and they are all solutions of just GL in D equals 4. And all of these black holes possess a black hole horizon geometry which is spherical. So there are also some theorems that not also constrain the proliferation of black holes, that also tell us that black hole solutions in D equal 4 in general relativity must possess a spherical horizon. And even more, we know that for all of these, we know that, for example, in GR, we have some conjectures that complicate also to find black hole solution when we include matter fields. So there are some theorems or some conjectures called the non-Hertz conjecture that complicate to find black hole solution when the geometry interact with matter fields, for example, scalar fields or electromagnetic fields and so on. And this conjecture named the black hole non-Hertz conjecture, states the following. So it says that the final state of a black hole after collapse is described only by two parameters, which are the mass, the charge, and the angular momentum of the black hole, and that any other quantity is regarded as Hertz and must be either expelled out or eaten by the black hole after collapse. So, for example, let us consider a neutron star that is going into collapse, to gravitational collapse, and that neutron star will possess a mass, probably charge and angular momentum, and there will be also several fields or futures of this field that will be around the neutron star when it is collapsing, like, for example, Byron's and lepton number and so on. This conjecture, which is mostly based in the uniqueness theorem that I showed you before, that I told you before, will tell us that the final state of this neutron star after collapse will be described by a black hole that can be described only by mass, charge, and angular momentum, and any other of these quantities that could in principle describe the black hole at the end will be rolled out. Okay, so that is basically the principle behind the non-Hertz conjecture, which we need to also uplift to a mathematical theory. So let me show you a more mathematical example of how we realize this in nature, in the sense that how do we know that a specific gravity theory will not provide us with black hole solution that depart from the family of solutions that we can found based on these uniqueness theorems. So a typical example, I know there are a lot of formulas, but I will go fast. So a concrete example is the well-known Bekenstein non-Hertz theorem that you can find in this archive code. So let us consider that apart from general relativity, we supplement the space-times with scalar fields, minimally coupled scalar fields, okay? So no non-minimal coupling. So let us consider a massive scalar field, where this is kinetic term, and where this B will denote the potential of the solution, will be basically the mass. So this is the action of the scalar field. If you compute the equation of motion, it will give you the Klein-Gordon equation, okay? And let us consider that the scalar field do not depend on time, and that the space-time is asymptotically flat. That means that when I'm going to infinity, there is no curvature of the space-time. If we multiply this equation of motion by phi, by the scalar field, and we integrate by part, we obtain this equation where we have this bulk term and this boundary term. It is easy to evaluate the boundary term, which is composed by the term at infinity. So the boundary of this space-time solution will have a term at infinity and a term of the horizon. So we need to evaluate both of them. If we compute the boundary term at the horizon, we will see by using the Schwarz identity that that term is going to be 0 because the horizon is a null hypersurface. This means that the vector that gives me the direction that points toward the surface is null, so its norm is going to 0. Okay, so that is the reason why the term at the horizon is zero, let's say. So then we need to evaluate just the term at the infinity, and if we consider that the scalar field goes at the infinity is 1 over r, we observe that there is also no contribution from the term at the infinity, so we left only with the bulk term. And we will see that because of our equation of motion, this term needs to be zero. This is positive, and this will be positive if we define a positive potential. So each time we are considering a well-posed potential, we will see that the only way to satisfy this equation is that the scalar field must be trivial. So either zero or the derivatives of the scalar field must be zero. So that is telling us in a mathematical way that we cannot find black hole solutions where the scalar field outside the space-time is non-trivial. Okay? So that is a mathematical representation of this non-Hertz conjecture statement. But how do we look for black hole solutions when we depart from this, from general relativity, or even in general relativity plus cosmological constant? We need to do something to obtain solutions, and we need to find some way to circumvent this kind of theorem. So first of all, we know that there is no a general non-Hertz theorem. So every theory that we are analyzing, we need to check it. We need to analyze it by independently. Let's say, I mean, for each theory I am considering, I need to see if there is a non-Hertz theorem to be considered, and to see how I can circumvent the theorem to look for black hole solutions. There is also always the possibility to include non-minimal couplings. We can also include a non-trivial cosmological constant, which gives us the opportunity to circumvent the topological theorems. We know that in GR plus cosmological constant is equal 4, we can obtain solutions where the horizon of the black hole is not spherical anymore. We can obtain black holes with planar or hyperbolical horizons. And we know that also if we go to higher dimensions, this means that we are not working anymore in 4 dimensions, we go to d equal 5 and so on. Higher dimensional gravity avoid uniqueness theorem. That means that I can find new solutions apart from the Newman family when I'm going in dimensions that are greater than 4. Okay? And that is nice, and that is what I'm going to show you in the context of black string solution, which is a kind of black hole which possess extended horizon. That means that the horizon now looks like a cylinder in higher dimensions. That is a particular property of higher dimensional scenarios, because the phase structure of black hole solutions in higher dimension is greater than in GR. So why we should consider higher dimensional gravity, or why higher dimensional is attractive? So first of all, as I told you, there are black hole solutions with non-spherical horizon, something that we cannot find in GR without cosmological constant. There are extended black objects with horizon presenting dynamical instability, so we can find for compact objects whose horizon is unstable. And there are richer structures also in d greater than 4, due to the fact that rotation adds new dynamics, because now when we are going to higher dimension, for example 5, 6, or 7, we have more plane of rotation. So we can rotate in different planes, and that also gives us a richer structure of higher dimensional solutions in GR. So as the title of the talk said, I'm going to talk about about some objects that are dubbed black strings and black P-branes, and I will show you what is a black string now. So let us consider general relativity in 4 dimensions. The static and charged black hole solution of GR is the well-known Schwarzschild black hole. And this is the metric of the space-time that represents geometrically the Schwarzschild black hole. The horizon topology, as we know, is the topology of a 2-sphere, so S2 topology. If we go to higher dimensions, if I uplift this solution to any dimensions, we found something which is called the Tangerlini solution, and which is the higher dimensional extension of the Schwarzschild black hole, where now the horizon possesses the geometry of a higher dimensional sphere d-2. But because the fact that the uniqueness theorem are not holding anymore in d equals 5 and greater dimensions, for the same theory we can find another solution which is not the Schwarzschild black hole or the Schwarzschild-Tangerlini black hole. And this solution is known as the black string solution, or the black pre-brane or Q-brane, as I call it here, solution. So let us consider d equal greater than 4. In fact, for a space-time of dimension capital D, which can be divided in d dimension plus q extra extended directions, we can find a new solution called the black string, and this is the way in which this works. So let us consider this cylinder I have here, and let's say that we live on this four-dimensional space-time. So we have a black hole here, the Schwarzschild black hole. And let us include in the space-time extra direction which are extended, like the zeta direction on the cylinder, okay? So in 5 dimensions, not only the 5-dimensional version of the Schwarzschild black hole exists, but also this kind of solution, which is the black string. And this is the metric of the black string. You see that the space-time that lives on this region is given by the black hole in dimension d, let's say 4 dimensions, for example, plus a q extended extra direction that you can include in your space-time. That is a black string, okay? So it looks like a cylinder. And this solution, of course, can be generalized to q extra extended dimension, and in that case, we call it the black string, black Q-brane solution. But what is the principal feature of this solution is that it, first of all, show us that in dimensions greater than 4, the phase structure of the solution is much richer than in 4, because for the same theory we can find different solutions. But also it's telling us that in higher dimensions the event horizons no longer they don't need to be spherical like in D equals 4. Even if the solution is trivial to be constructed, because it's trivial to include a flat direction space-time, the equation of motion are easily solved because in the extra dimensions the curvature tensor are going to 0. We see that there are some obstruction when we are including cosmological constant or electric charge. For example, if we want to construct this black string version of the Schwarzschild ADS black hole, then we cannot do that without including a non-homogeneous factor on the metric. That means I have Schwarzschild in D equals 4 without cosmological constant. I include in my space-time an extra extended direction. I found the black string. Now I take general relativity plus cosmological constant. I know that my black hole of that solution, of that theory, is Schwarzschild ADS black hole. If I include extra extended direction, then I cannot construct the black string. So it's an obstruction in the fact that we can, there is no possibility to construct the IDS Schwarzschild black string in an easy way. Of course, if we cannot construct the Schwarzschild IDS black hole, there is no black string version also of the BT zeta solution, which is the Schwarzschild IDS black hole in 3 dimensions. And there is also no black string version of the Rydell-Nostrom solution, which is the Schwarzschild black hole when we include electromagnetic charge on the spacetime. So let me show you how that works, why we cannot construct solution with black string solution with cosmological constant. So let us consider Einstein equations that come from Einstein-Hilbert action, which is plus cosmological constant. It means Ricci scalar plus cosmological constant in an arbitrary number of dimensions. So if we compute our equation of motion, this is the solution, this is the Einstein tensor, and this is the term proportional to the cosmological constant. So let us take the trace of these equations on the black hole slide of the black string. This means here. Let us take the trace of the equation on this slide. If we do that, we will see that the Ricci scalar must satisfy this formula. So it's related to the dimension of the space-time, the dimension of the slide, times the cosmological constant. On the other hand, if we compute now the same Einstein equations, but on the direction zeta, in the extended direction I have included, we will obtain that the Ricci scalar must satisfy this constraint. So if we plug this constraint into this equation, we will see that the only chance to satisfy both equations at the same time is that the cosmological constant must be 0. So that is why you cannot construct black string solutions with cosmological constant in an homogeneous fashion way, let's say, okay? So and if you do the same but consider electromagnetic fields, you will arrive to a similar obstruction. So the equations on the slide and the equation on the extended direction are not compatible. So let me show you a way to avoid this problem and to construct properly homogeneous IDS black strings. So let us consider Einstein gravity again, plus cosmological constant, but let me just include on the space-time minimally coupled scalar fields. If we do, these are the equation of motion, so Einstein plus cosmological constant, but minimally coupled scalar fields, well, this is the well-known energy momentum tensor for minimally coupled scalar. Of course, each scalar field must satisfy the the Klein-Gordon equation, and we also will suppose that the scalar fields depends only on the extra directions I include in the space-time. So they are not dependent on t, on r, or any dimension which lives on the slide of the black hole. They will depend only on zeta or any other dimension I could include. If we do so, okay, I will skip this part, then you can ask me why we decide to use this kind of scalar field in particular, but because of time I will move. So if we compute the equation of motion for this system, if we solve this system by applying into the system the metric of a black string, so the metric of a black hole plus q extended directions, and we consider that the scalar fields depend only on these extended directions, you will solve the equation and you will see that the metric is precisely the metric of a Churchill ADS black hole, this one, in arbitrary dimension, but where the cosmological constant factor, this factor which is here, now acquire a contribution from the scalar field. So this factor will depend on the number of extra dimensions I will include in the spacetime. And we will see that there is a relation that must be satisfied, which is something that relates the axionic charge or the scalar charge that appears when you integrate the Klein-Gordon equation with the cosmological constant. You will see that in order to get a real scalar field, you need to consider negative cosmological constant. So what we found here is basically the Churchill ADS extension of the black string version of the Churchill ADS black hole. So the solution above is the first of this type of having been found analytically. This means that and in an homogeneous fashion way, it's analytically, and solve the Einstein equation with a non-vanishing cosmological constant. So the space-time will be asymptotically ADS in d dimension times the line in q dimension, or the q plane. And the curvature radius will be given by this factor. So of course you will recover the typical IDS factor when you set q equal to 0. And because there is no obstruction, there is no problem when setting d equals 3, you are able to find the BT zeta black string version of this solution. This means you can take a three-dimensional black hole and put it in form in the shape of a black string. This also can be done in the context of quadratic gravity, that means some theories of gravity that contains quadratic contributions in terms of the scalar curvature, like this one. These are the two contributions that you can construct with two scalar tensors, with two curvature tensors. Of course, can be included any contraction of two Riemann tensors, but they are not appearing here because you can integrate them by part, and then appears the Gauss-Bonnet contribution, which gives 0 in d equals 4. And we will see that also this black string solution can be embedded in this theory. But the question that arises, can we include electromagnetic charge? And we can do this, but we need to go to more general gravity theories, like for example Lovelock theory. So in order to put also charge on these black strings, in order to obtain something like a black string version of the Rydell-Nostrom black hole solution, you need to go to gravity theory that contains higher order powers of the curvature. I'm not going to say, one way or one theory, one well-posed theory in higher dimension that gives you second order equation of motion, even if you include higher curvature term, is Lovelock theory. And Lovelock theory is given by this Lagrangian, where this is a combination, it's a sum of this term, which is a generalized curvature term that is given by contraction of a totally antisymmetric delta Kronecker delta with curvature tensor. If you go to order 2, you get something which is called the Einstein-Gauss-Bonnet gravity. That means that the 0 terms of that expansion give you the cosmological constant, the term n equal 1 gives you general relativity, and the term n equal 2 gives you the quadratic version of the theory, which gives this Gauss-Bonnet term, plus blah, blah, all the contribution that you can obtain expanding that sum. And it was shown that one way to obtain charged black strings is precisely to consider only a single term of this expansion plus a content of matter that is called p-forms. So if you include, instead of a scalar field, a generalization of this field which is called p-forms, you can construct charged black hole solutions only if the single term of the Lovelock expansion that you consider has the same order that the p-form you are considering. For example, and I'm about to finish. So let us consider a pure Laplace term of order n. So let us take any term of this expansion of order n, but just one, not the full series. And let us consider p forms. And let us consider the action of a p forms. The equation of motions that we need to make compatible, this means the equation of motion on the black hole slide and the extra directions, will be only satisfied at the same time if the order n of the Laplace expansion that we are considering is equal to the order p of the forms. When n is equal to 2, the gravity theory is given by Gauss-Bonnet theory. And when p is equal to 2, the form is given by the Maxwell action. So one way to construct charge solution is to consider Gauss-Bonnet theory. And that was made in this paper, and the author has they were able to construct black string with charge in dimension greater than 6. But can we include cosmological constant? We can apply the same trick I did before for Schwarzschild black hole, and doing so you are able to construct asymptotically ADS homogeneous charged black string, now in pure Laplace theory. And of course we obtain a constraint between the charge, the action charge, and the parameter of the theory. Can we do the same but including the homogeneous Laplace series? That means consider cosmological constant, Einstein term, Gauss-Bonnet term, and any other contribution? Well, that is something that we are working now, but we need to include more exotic coupling for the action. Now the scalar field that we include in the space-time are no longer minimally coupled. We need to include kinetic couplings between curvature terms and the derivatives of the scalar. So let me just remark on future directions. So what are we doing next? We are trying to see if these black string solutions can be embedded in f of r theories and try to decide which form of the function f are able to support this kind of solutions. We are trying to see if this black string also exists in more general scalar tensor theories. So when you are considering a Lagrangian for the scalar field, which is more general with kinetic couplings and so on, we need to study the instability, because we know from the GR counterpart of these black strings that they have instability. That means that when you are in D equals 5 dimension, you have the black hole and the black string, but the black hole possesses a bigger entropy. So from a thermodynamical point of view, the preferred phase of the space-time will be the black hole and not the black string, and that gives us the insight that there is a mechanical instability in the black string. So it is going to happen the same when we include cosmological constant, something that we need to see. And because we have included this particular kind of scalar field, I didn't say what, or I didn't say why. This kind of scalar field gives us the opportunity to study some holographic properties of this solution, to study phase transition, and also to generalize the black hole thermodynamic, that you can work on these black holes. Thanks. That's it.
Thank you for your contribution. Any short questions?
Thank you for your interesting talk. I would ask, can this black string be also a valid candidate for dark matter? And if yes, have you thought that if you try to recover this object in F-O-R theory, you can have both dark energy and dark matter through this?
Okay, to be honest, when you are constructing this kind of solution, you are not thinking application in cosmology. So they are compact objects as much as black holes. So probably you consider that dark matter is given by this kind of object. They in principle should exist. So far, we know that the black string constructed from the Schwarzschild solution is unstable. So in nature, what should be realized is the black hole, not the black string. So I would say that no, they will not be candidate to dark matter so far, even at least if you don't find any stable black string solution at some point. And what we are looking now in the context of F4R theories is, well, as I show you here, we consider also the construction of this object in quadratic theories of gravity. So we can replace this for an arbitrary function in terms of the rich scalar, the rich tensor, and so on. And what we want to do is to reconstruct the most general form for f such that these solutions exist on that theory. Not, I mean, we are not thinking about to dark matter or dark energy, to be honest.
Okay, there are also other theories of gravity, for example, infinite derivative gravities, in which the horizon, in four dimension, for example, is replaced by a shell which divides the non-locality from the locality region. So in a certain sense, black holes do not exist in these theories. But do you think that you can obtain black strings in these cases even though black holes are not present? I mean, just curiosity, maybe.
Yeah, I'm not aware. I'm not aware of the details of that kind of theories, but even if the structure of the black string is different from the one of the black holes, there is an horizon inside. So I will say that no. But the difference that, let me go to the picture. So a typical, let's imagine that we are in 5 dimensions. So in 5 dimensions, the Schwarzschild solution, or in 4 and whatever, will have an horizon, will possess an horizon which is which defines a black hole. So you need an horizon to define a black hole. And the shape of the horizon will be a kind of 3 sphere. Okay? What you are changing when you are looking for black string solution is that now you will be in a 2-dimensional sphere which possess also an extra extended direction that will modify the shape of your horizon. But at the end, what you have is also a black hole but with a different horizon, with a different topology. So the horizon is still present on this kind of solutions, like this one.
If there are no more questions, let's thank the speaker again. The last speaker of this session is Lasha Dalakishvili from the Tbilisi State University. And he will talk about the stochastic resonance in this stable state.
Hello, I'm Lasha Dalakishvili from Tbilisi State University, and my task is about the bistable systems and the stochastic resonance. So before I start my task, I want to talk a little about the noise. Well, we always thought that the noise is bad, it is irritating, it erases the memory, and it is the opposite of regularity, but recent studies show that in some cases noise can be very useful. And furthermore, in some cases, some specific cases, it increases the regularity and it makes the effect of weak periodical signal stronger. And that effect is called as the stochastic resonance. Let's take the ordinary bistable system which plot is on the slide, and write down the Newton's second Lloyd's equation. And also we will have the force of the friction and the friction and the dispersion coefficient theta, the nonlinear coefficient alpha, the weak periodical force F, and the Xi, which is the random force with amplitude is beta. For the first time, let's take the white noise distribution and see what happens. Well, we all know that white noise has the equal density for all the frequencies, and if that white noise is very weak, there is no effect. So the system stays only in one hole, and it has only one state. If the random force is very high, the system starts moving from one state to another, but this movement is not regular. But if we will take these parameters which are written on the slide, we will clearly see that the system starts moving regularly from one state to another, and this movement is because that we added some white Gaussian noise to the weak periodical force. And we will have the main parameter, which is key, well, this one. This one, which is the ratio between the amplitude of the white noise and the dissipation coefficient, and this one remains the same. So if we change the dissipation coefficient, we have to change also the amplitude of the noise doubly, because this C is equal to 2. So then I changed the type of the force, and it was no longer harmonica, but I took the square impulse, and here the result is very interesting, because the movement and this effect is becoming more and more stable, and our C is very large. So it is not 2 or only the one parameter, it becomes 11 or 14. So C can be any C can be any number for 11 to 14. So that means that if we have more static force, we will catch this effect more easily. And this effect we can see for the square impulses as well as for the harmonica, so for the cosinus or sinus. But well, how can we see the difference between these two plots? We can say that one of them is sinus or one of them is square impulses. So if we have the two graphics, we can say who is who, how to say. And here we need the informational entropy, which gives us the clear number of the random information which comes to us from this system. Well, to explain it more clearly, let's take this sentence and mess up all these symbols. So we will have the ocean of these symbols, and if we took these symbols randomly, we can build from this ocean the sentence which is written on the slide or any other sentence. So that means that the process and the chaotic data can bring the more information, and we just have to build them. And every new sentence which we will build will be the surprisal. So it is called the surprisal information, and the surprisal information is equal to entropy of the real system minus the entropy of the regular system. So if this information goes to 0, we can say that the movement from chaotic becomes that the movement moves from chaotic state to the regular state. And it seems that the cosinus is more non-stable than the square impulses, so it always brings us more information, more surprisal information than the square impulses. So if it can work for the white noise, why can't it work for the other types of the noises? For example, the pink flicker noise. I took this flicker noise because the flicker noise is most widespread noise in the nature. The waterfall generates the flicker noise, the cars in the traffic generates the flicker noise, which density is 1:F, so it is higher if the frequency is low, and as we go up to the higher frequencies, there are more empty space, so the density is becoming less and less. It appears that it also can work for the flicker noises. The linearity always remains in such cases, and there is some interesting fact that if we take the C as the ratio of the white noise amplitude and theta and C1 as the peak noise amplitude, And theta, their ratio always remains the same, and it is about 4, no matter of what is non-linearity. So the non-linearity here was equal to 1, here is equal to 5, here is equal to 20, and for every non-linearity they are changing separately, but their ratio remains the same. So here are the conclusions. That it can work for the other types of noises, and linearity remains, and for square impulses, the flicker noise amplitude and the white noise amplitude remains the same, no matter of non-linearity. But if we look at the previous slide, we will see that the information has changed. So it was always about 0.2, and now it's 0.1. So we need one more characteristic to describe our system and find out which type of noise or which type of regular force we have. And so here we need the recurrence plot, which gives us the clear visualization if the system periodically repeats itself. So we have the data. Let's take per second. Per second, we will have the x, the coordinate which is given to us, and when, for example, xe, so the x, the coordinate is the time which is ae and which is kg. So let's wait. Sorry.
No worries.
Okay. So let's say that the x is equal to the 0.5. If we have n, which if it repeats itself for 10 times, we should divide this time in 10 equal times. So if the time is 30, the time t1 must be 3. And we will see does our system repeats itself in after every 3 seconds. So we must see what was x on 0, then on the 3, then on the 6, and if it will repeat itself, there will be the grid because there will be the point. If it does not, so if we have the chaotic motion, that means that we have no regularity, that we have no periodic, and so there will be just points and between them the empty spaces. So we can clearly see that if we have the sinus or cosinus, the grid is becoming like a chessboard. And if we have the square impulses, there are more empty spaces, but the grid, but we can clearly see the grid, which does not look like the chessboard. Here also is the puzzle plot. On the x label there is a coordinate, and on the y level there is the impulse, and we clearly see that the system has 2 regular states, and our puzzle point is moving from one state to another. And then what I thought, what will happen if they put the chaos not only in the external, so we don't add it only artificially, but we put the noise in the periodical force itself. So I took the random phase, and it appeared that that if the amplitude of the random phase is small, they remain still, the effect remains the same. So we still can see the effect of stochastic resonance. And here also is quite a linear correlation, which was quite interesting between the internal noise and the external noise. Here, the B1 is the amplitude of the phase, which is in the periodical force itself, and B is the amplitude of the white noise, which we add to the system. I tried this as well as for the flicker noises, as for the square impulses, and these square impulses, we also have the linear correlation between them. So, well, I tried that also for the Lorentz system, but I had no any interesting solution, so I'll skip this thing, and I will go closer to the conclusions. So at first we had the weak periodical force with the harmonic force, and also as well as for the square impulses. Then we added the chaotic force to this system, which has the white noise distribution, and we saw the effect of stochastic resonance, which involves itself that the effect of weak periodical force became stronger. Then we changed the type of the noise and added the flicker noise. And we also saw this effect, and we also saw this effect if we had the internal noise or the external noise, and every correlation between the parameters were linear. That's all. Thank you for your attention.
Thank you for your contribution. Any question, comment? I have a curiosity. Do you have an idea if your consideration about noise can be applied to the work of the first speaker of this session?
Maybe it can, because we both have the noises, but I tried a little bit different types of noises. Here, the construct noise, and I tried some flicker noise and also the white noise, but maybe there can be some correlation between his movement and the movement of the stable system.
Okay, thank you.
You're welcome.
So if there are no questions, let's thank the speaker again. Now there is a lunch break, and the next session will start at 14:15. Thank you for your attention.